Okay, we're going to explore this morning, at least for the first hour or so, some consequences of unitarity. And unitarity is a rather remarkable statement. First of all, unitarity is just the statement that probability is conserved, and it follows from the fact that the S matrix is a unitary matrix, and as I've mentioned, is a gigantic matrix, taking you from every initial state to every final state at every possible momenta. And clearly most of the elements are actually zero, but the ones we are interested in, of course, are not. And though it's a complicated relationship, if we have, and we'll come to something more complicated than this shortly, but if we consider elastic unitarity, which means we consider some process AB goes to AB, then this tells us that the imaginary part of the partial wave amplitude as a function of the energy squared is equal to some factor which depends on energy times the modulus of that amplitude squared. And it does it, very importantly, for each partial wave amplitude. In other words, this is a very, very complicated relationship, but if you decompose it into states which have definite sets of quantum numbers, definite angular momentum, for example, then you see that it provides a relationship between the same values of L. It doesn't couple L to something else, it's diagonal in angular momentum. And that's one of the reasons for studying partial wave amplitudes, because unitarity is simple. What happens when they're more than just what elastic unitarity we'll come to a little bit later. Now this function rho is equal to, if the masses are equal, well let me assume all the masses are ma equals mb equals m, then this factor rho is just equal to the square root of s minus 4m squared. Well, sorry, I have written something else first, so let me do that. It's always equal to 2 times the center of mass momentum of the final state divided by root s, and if the masses are equal, then that's just s minus 4m squared over s. And this factor, what you notice immediately about it, is that though it's 0 at the threshold, it very quickly goes to 1. So asymptotically, it goes to 1. So this function, as a function of energy, each of these phase space factors, here at 4m squared, or whatever the threshold is, it's 0, and it goes to 1 as a function of energy. Now, just to make a link to what we were discussing yesterday, this imaginary part starts at the threshold, okay? This is when this factor is non-zero. Below the threshold, below the lowest threshold, the amplitude is real. So the reason for looking at the example that I considered yesterday, g of s, which was equal to the square root of the threshold minus s, and looking at its analytic structure and seeing that it has cuts in it, is because this is the simplest function that looks like this function, which has the property that when s is below the threshold, it's real, and when you go above the threshold, has an imaginary part. So it's an example of a function that has a non-zero, is real below the threshold, and has an imaginary part above the threshold. And in fact, these TLs have such a factor contained in them, and all this factor S on the bottom does is makes it go to 1 asymptotically. Okay. Now we're going to explore the consequences of unitarity a little bit further, because the world is not elastic unitarity, there are clearly a very large number of channels. But before we do that, it's useful to consider the Breit-Wigner form. Is that the right spelling? Yeah, right. Or is it the other way around? It's the other way around, isn't it? Now, where does this come from? The Breit-Wigner form of a resonance is an approximation. And it's an approximation based on what the propagator looks like for a real particle. So for a particle like the nucleon, so a particle of mass m, its propagator is related to the Fourier transform. I hope I can get this the right way round. Is the Fourier transform of e to the imt, because the wave function of something, a real particle, would be e to the imt. And forgetting about the i's, you can see that this is equal to m minus e. So the propagator in momentum space of a massive particle is just its mass minus its energy if it's non-relativistic. So a particle of mass m non-relativistically. We'll worry about what happens when it's relativity in a minute. Now, a resonance is an unstable particle. And so its wave function is not just e to the imt, but it's e to the minus mt times a part which decays with time. And its decay is labeled by, you could write t divided by the lifetime. And instead, we write it in terms of a quantity gamma, which is the inverse of its lifetime, to have the same dimensions as mass. So gamma is something we call the width. Why it's the width will become clear in a minute. And then, if you take its Fourier transform, the propagator is 1 over m minus e minus I gamma over 2. So an unstable particle is not a pole on the real energy axis, which the nucleon would be, a proton would be, but it's at some complex value where its how complex it is related to its lifetime. Now, when we make this, do this relativistically, essentially, instead of the energy, we write the square of the energy, S. So imagine this is in the center of mass frame, and then you go to do this properly, and you can read in textbooks how to do this. So relativistically, the propagator, or the relevant partial wave amplitude, it's the same. The propagator becomes 1 over m squared minus s minus im gamma. That's how we usually write it, where s is just equal to e squared. Now, they're not exactly the same, as you will notice, because m minus I gamma over 2 squared is m squared minus im gamma, but there is also a piece gamma squared over 4, and that's just absorbed into the definition of m squared, essentially. So for a particle that's almost stable, or it doesn't make any difference. So the Breit-Wigner formula is related to this. It would be that the partial wave amplitude would be equal to some quantity. I'll tell you what the factors are in a minute. That the amplitude would be equal to this, where in the partial wave amplitude there are couplings g at the two ends if it's an elastic process. So AB to AB, the coupling to AB would be g, and then this propagator would be this. Now, that formula doesn't satisfy, at the minute, elastic unitarity. One of the properties that's not, well, it will do, let me maybe say, in general, m and gamma are themselves functions of S. Functions of S. Now, that may not immediately be obvious, but we'll see why in a minute. We usually treat them as constants, or very often, but we can immediately see that at least gamma has to be a function of S, because to satisfy unitarity and satisfy that equation, gamma must contain a factor inside it, which is rho, because the imaginary part of the amplitude comes with a factor that looks like this, and so gamma itself must contain such a factor. So to make it satisfy elastic unitarity, we want to keep some of these things. So let me remove this bit maybe. We replace the most obvious one is that we replace gamma. Gamma is a function of S by rho times gamma. And then elastic unitarity, if it's an elastic resonance, would tell you that the partial wave amplitude, if it was just given by a Breit-Wigner, would be m gamma over, sorry, I should call this capital M, m squared minus S minus I rho m gamma. And you can easily check that that satisfies that equation. And all I've done is essentially multiplied the width by a factor which is almost 1, but it switches off at the threshold. Now, let us look at what this amplitude looks like. We showed that if you define a quantity little tl, which is rho times capital TL, then this can be plotted. So this is the real part of TL. We don't really need the L, it's just a label for angular momentum. That if you remember, this is supposed to be a unit circle, and if elastic unitarity is satisfied, the amplitude moves round the circle. And that's exactly what this function does. And it has the following shape. So let me draw that over here. What you can see immediately is that when S is equal to m squared, so m is a real number, when S is equal to m squared, the amplitude is purely imaginary, and if you multiply by rho to get rid of this factor here, you see it's equal to 1. So at S equals m squared, the amplitude is at the top. So if we were to plot what the modulus of TL looks like, it looks like this. Some shape that looks like that, where the peak is at S equals m squared, and at that point, if it's elastic unitarity, this quantity is equal to 1. And what does gamma do? Well, gamma tells you if you go to half the height, it's essentially, well, m times gamma, if I plot it in terms of S, is what that distance is. So depending on how this amplitude goes round the circle, And how fast it goes obviously depends on the lifetime of the state. So if it's very long-lived state, then this is very spiky, and it will go round very quickly. If it's a short-lived state, then it goes round more slowly, and the amplitude looks like that. Now, there is another piece to this which I haven't told you, which is that was treating. Oh yes, let me do that. Let me do something else, which is that as a result of the amplitude going round the unitarity circle, you remember, I hope you do, that the partial wave amplitude of its elastic unitarity can be written as sine delta e to the I delta, where delta is called the phase shift. And we can plot the phase shift. And what does the phase shift do? Well, the phase shift does that. So this is pi at the top, and here at m squared, the phase is pi over 2. Okay, the amplitude is going round the circle, and when it's at the top, it's phase. If it's elastic, then this angle is delta. And then the phase at the top here is pi over 2 at the resonance mass, and then it goes to pi. Now, there are a fourth thing. Let me call this one number 1, and this property number 2, and this property number 3. The property number 4, which follows from this formula, is that if we look in the complex S plane, so here is the real part of S along here, and the imaginary part of S is here, that this corresponds to a pole, namely the denominator is equal to 0, at some point here. And where you do your experiment is along that line, essentially just above, along the real axis, because energies are real. And by convention, they have a plus I epsilon, which tells you that they're just above. Now, the Breit-Wigner formula, for if the resonance is elastic, satisfies those 4 properties, and they're all equivalent to each other. So if you measure the cross-section, which is what this is related to, you see a peak in the cross-section. If you could measure the phase of the amplitude, you would see that as you go past the resonance, the phase changes by pi. You can see that in this denominator here, because when S is very much less than m squared, then this is a real, effectively it's dominated by this factor, and it's real. And when S is very big, so you've gone right past the resonance, this piece wins, and it's got a minus sign. And so because of that, the phase has become pi. So as you go past the resonance, the phase changes. The angle where you do your experiment to the resonance, that's a small angle, and when you've gone at high energies, you're looking back at the pole, and it's looking back through an angle pi. So the phase changes from 0 to pi, and there is a pole in the complex energy plane. All of those are related to each other. Now, they're only related to each other in a very, very special case. They're related to each other when a resonance is isolated. There are no other resonances nearby, sitting somewhere else, very close. Or there are strongly coupled thresholds near to the resonance. Then the phase doesn't necessarily change by pi, it's more complicated. There may not be a peak in the cross-section. There can even be a dip in the cross-section, depending on what is happening. The only thing that tells you that there rarely is a state in the spectrum is that there is a pole in the complex energy plane. This is always true if there is a resonance, but these other facts only happen if the resonance is well separated from all other resonances and all other there are no strongly coupled thresholds nearby. So these are connected. So properties 1 to 4 hold for an isolated resonance. Unfortunately, there are some examples of isolated resonances. The ones that we've known about for longest. In general, it's the pole in the complex S-plane that tells you, that implies a state in the spectrum, an unstable state in the spectrum. So the Breit-Wigner formula encapsulates this, but it's an approximation. And it's an approximation that's true in the neighborhood of this pole. Then you can treat M and gamma as though they're constants. But if the state is very short-lived, and so the pole is a long way away from where you do your experiments, then the mass and the width will be functions of S and will change rapidly. And so, though the amplitude here in the complex plane will look like it's got some denominator like this, what actually you see on the real axis may be something more complicated. So let me give you a couple of examples. The one that is probably, there's one other property probably that I should mention, which will help, I think, is that I mentioned that this gamma contains a factor of rho, which is what this factor is here, and tells you that as you approach the threshold, the amplitude goes to 0. But it does something more than that. If the momentum p goes to 0, then gamma behaves, in fact, like p, in fact, to the 4L plus 1. I think that's correct, yes, gamma behaves like 4. So the 1 comes from this factor, because that contains a factor of momentum. So it goes to 0 very fast at threshold. So let me draw a couple of illustrations of elastic resonances. So the rho resonance, which is seen in E plus E minus annihilation, but couples, for example, to 2 pions, it looks, let me make a long axis like this. So here is pi threshold, 4m pi squared. And then the rho resonance, or the modulus of the amplitude, it has L equals 1 for the rho. The modulus of the amplitude indeed looks very nicely like a Breit-Wigner resonance, where this would be m rho squared. And the rho essentially only couples to pi, and because of these factors, it's suppressed very close to the threshold. So it looks very nice and peaked. The next resonance that appears sits somewhere up here. It's not essentially elastic, but it sits somewhere here. In fact, it's fatter, but doesn't matter. The next resonance, let's say, is here, and these are well separated from each other. And so in the analysis, for example, that Antimo Polano was talking about yesterday, in which he treats all amplitudes as though they're just resonances given by Breit-Wigner's and some background amplitude. It's not a bad approximation, provided these resonances are well separated from each other. We look in the spin 2 amplitude with L equals 2, then there is the same threshold, but now, because of these factors, these are even smaller, and the resonance looks something like that, and this is called the mass of the F2 squared, the lightest of the spin 2 resonances. So now, if you see that in the experimental data, you have no doubt you have seen something that looks like a state in the spectrum. It turns out that this state, this one is exactly elastic, so the modulus of the amplitude goes up to 1. This one is quite elastic, and it goes up to 0.84. So it's almost elastic, but not quite. So though I've drawn it bigger than that one, it isn't actually. It's a bit smaller. So it doesn't go quite up to the top of the unitarity circle. But if, on this plot, I were to draw what L equals 0 pi amplitude look like, because there's L equals 0, the only factor of momentum that appears is one factor of p. And then if I draw it on this scale, the amplitude looks like this. So this is the modulus with L equals 0 in pi to pi. You see, it looks completely different. Now, why is that? In fact, it turns out that there are two states in the spectrum here, one called the sigma and one called the F0980. If two resonances are well separated from each other, you can add Breit-Wigner's to each other and still satisfy unitarity. But if we go back to our unitarity circle, imagine you have elastic unitarity, and you have one resonance which says the amplitude's got to go round like that. But before that resonance is finished, another resonance starts. Then clearly, if you just add two Breit-Wigner's to each other, you get an amplitude that doesn't go round the circle anymore and violates unitarity. In fact, what is happening here is that there is a very broad resonance and then a very narrow one that sits in the middle of it. And because it sits in the middle of it, it actually causes a dip in the amplitude or dip in the cross-section. So it's like one resonance on top of another one. So if you were to add two Breit-Wigner's, attempt to add two amplitudes together and force them to satisfy elastic unitarity, then you would find that you have exactly this kind of structure. This corresponds, this is not a random place, it happens to be at kk bar threshold. So at 4 mk squared, I should really write. And that's because the second resonance couples very strongly to the kk bar channel. So essentially, what has happened is that there is one resonance, the first one, where the amplitude got to the top and then sits on top of it another resonance, but it starts at the top. So it goes round like that, and where the resonance mass is near the bottom and causes that dip. And this meant that there was a very long time before exactly what this structure was understood. So this is due to something called the sigma and this is something called the F0980. And the fact that the dip appears exactly near kk bar threshold is what tells you it likes to couple to kaons. Now what you see, and what the message I want you to take away, is that just when you see a peak, it very often is a resonance, but there can be states in the spectrum where you can even have dips and they correspond. It's what determines are the poles in the complex energy plane. Those are the properties that you need. Now the states that are simplest, the rho, the F2, in other words, the lightest states with the biggest spin that they can have at that energy, are the ones that we can easily identify with the states in the quark model. Because the quark model essentially treats decays as though they were perturbative. So in the quark model, the rho, which couples to pi pi, is given by, the amplitude is given by g squared over m squared minus s at lowest order. It's a stable particle. And you assume that the decays happen perturbatively, namely that you can add the part that corresponds to a decay, which corresponds to diagrams like this, which are ordered g to the 4 because they're 4 couplings. There's an imaginary part which related to phase space, divided by m squared minus s squared, and so on. And you add these contributions, and when you add them, you get a pole which is now no longer on the real axis. So at lowest order, essentially the sum of all of these terms, there's an infinite number of terms to add, is equal to this. And the quark model assumes that essentially you can treat these as perturbative corrections to those. Now that's not a bad approximation for particles that have the maximum angular momentum they can have for a given mass. So what happens is that if we look in the complex S plane, so here is the real part of S and the imaginary part of S. In a model like the quark model, at lowest order, the pole is on the real axis. That's where the pole is. And then when you add the corrections, the terms that come from these loop diagrams, and there are an infinite number of them, the pole moves into the complex plane somewhere nearby. Whether it moves up or down doesn't really matter for this, and there is a threshold, and there is a cut in the amplitude, because this is the first term that contains physical particles can be created. So the amplitude then has the right analytic structure, but the pole doesn't move very far because the interaction is a p-wave interaction, namely there is a suppression, the discontinuity across this cut, which determines how far the pole moves, is related to the angular momentum. It's related to these factors of p to the 4l plus 1, which are related to the imaginary part. And because it's a spin 1 object, this discontinuity is rather small near the threshold, and it doesn't move very far. But if you have an S-wave resonance, then there is no threshold suppression, and the pole can move a very long way from where the quark model has it. And so that's how you can get a very broad state, one that decays very, very rapidly. Okay, now let's try to go beyond elastic unitarity. Well, maybe before I get there, let me go back to the quark model a minute, is that here the state is just a quark and an antiquark. But as soon as you include these diagrams, the state can also couple to pi-pi. So now you have a mixture of a pi-pi configuration in the wave function of the state. And for the states where the quark model works best, which are those that are on what are called the leading Regge trajectory, like the rho, the F2 1270, and so on, they are very, very close. The movement, the effect of these extra terms is rather small, and they only make a small part of its wave function. It's still always dominated by its QQ bar component. And so those are the ones that are easiest to identify and connect to the quark model. That's always the case if the state has large angular momentum. So the higher the angular momentum that is required, the more these other effects are suppressed. And the ones in which they're the cases that look most Breit-Wigner-like. But other states don't need to look like that. So let's do what is called a coupled channel unitarity. There is not just one channel in the world. So what happens when there's more than one channel? If you understand how to get to two channels, then you know how to get to infinity. So the counting is 1 to infinity. If you know how to get to 2, it's obvious how to generalize it to any number. So let's consider the amplitude, an elastic amplitude. AB goes to AB. So an example would be pi n to pi n. The only thing I'm going to assume is that it's spinless. Of course, nucleons do have spin, but in other words, it doesn't have to be a meson amplitude. It can be equally a nucleon amplitude. Now, we saw that the imaginary part of the partial wave for a given set of quantum numbers, so L labels the orbital angular momentum, but it also labels all the other quantum numbers. It's true for each isospin separately, each parity separately, and so on. So we know it's equal to, we'll have to write this slightly more carefully in a minute, rho 1, the first threshold. So that's what we just had when it was elastic unitarity. And this is the process amplitude AB goes to AB. Now unitarity says that there is another contribution as soon as you cross the next threshold, and the next threshold for pi n to pi n is pi n to pi pi n. But it's easier to think about if we don't have multi-particles. Imagine the only channels in the world were pi n to pi n, and the next one was pi n, let's say, to rho n, as though the rho was a stable particle. The rho decays into 2 pions, so that's just easier to think about because it's 2 particles. It says, there is another contribution to this unitarity relation, which says when you come to the next threshold, you have to add the modulus of some other amplitude, and we'll do this better in a minute, where this is the amplitude for pi n goes to rho n. And this is the phase space, the threshold factor, for that channel. And you can imagine when you cross the third threshold, you have to do the same. So let's write these more generally, and then we can do a little bit of algebra with them. So unitarity, in terms of partial wave amplitudes, if this initial channel is I, and this final one is J, and this particular example was the amplitude AB to AB, so I was AB and J was AB. Now it says, unitarity, that the imaginary part of this, of that amplitude, is equal to I and J on the outside, and an intermediate state here which we'll call K, and you sum over all K, and you have to multiply by a phase space factor rho K. Now, what does that tell you? It says the imaginary part of the amplitude, let's do a simple example, is AB of the amplitude AB to AB, is equal to the amplitude for AB to go to AB with any possible intermediate state, and the requirement in the unitarity relation is that you only sum over physically allowed states. So K is any physically allowed states. By that it means you have to have enough energy to be able to grow. So there has to be enough energy for these to be real particles here. So the unitarity relation says that the imaginary part of the amplitude for AB to AB, let's say pi n to pi n, is equal to some phase space factor of pi n goes to pi n, goes back to pi n. That's what this modulus squared is here. But if you have enough energy, pi n can go to rho n, and then rho n can go back to pi n. And if you have yet more energy, there will be more intermediate states, and you can only include the ones that are kinematically allowed. In other words, you don't have to worry about the universe anti-universe being created in the middle here of virtual particles, or the moon anti-moon or something. It's only those that there is enough energy to create. So if we number the channels, label, so let's consider two channels. As I said, once you've understood two channels, consider two channels. Which we'll call 1 and 2. One could be pi n, the other one rho n. Or pi pi and kk bar, or whatever, many different examples. So then the unitarity relation says that the imaginary part of the amplitude for channel 1 to go to channel 1 is equal to the phase space factor for channel 1 times the modulus squared. That was elastic unitarity. Now remember, the labels label the channels. So that's when the intermediate state, if it's pi pi, the intermediate state is pi pi, goes back to pi pi. But if you have enough energy, pi pi can go to kk bar, and kk bar can go to pi pi. And because pi pi to kk bar and kk bar to pi pi are the same process, just time reversed, they are just the same amplitude. So rho 2 times T12 squared. And this is the threshold factor for channel 1, and this is the threshold factor for channel 2. But now, if you have enough energy that pi can go to kk bar, there are clearly other amplitudes. Unitarity says, in here we had the amplitude for pi to go to kk bar. But the amplitude for pi to kk bar also satisfies a unitarity relation. And it says that the imaginary part of the amplitude for pi to kk bar. So now there's pi on this side and kk bar on this side. And in the intermediate state, we can have pi and kk bar. So this is T11 star times T12 plus rho 2 T12 star T22. And then there is a third relation, because now we've got the amplitude for kk bar to go to kk bar, because pi can get to kk bar by going through a kk bar intermediate state. So the imaginary part of T22, kk bar to kk bar, also satisfies a unitarity relation. And it says the imaginary part of the amplitude for kk bar to get to kk bar, so there's kk bar on this side and kk bar on this side, can either do it through pi in the middle or kk bar in the middle. And that's what the sum of those two terms are. And once you've done that for two channels, then how to generalize it to more becomes obvious. Now, how do you solve those equations? We just saw a minute ago that when resonances, the world is not just resonances, they have backgrounds and so on. But where a resonance looks like this and another resonance is like that, well separated, then you can just add the two together. Not a bad approximation. But where resonances overlap with each other, you can't just add them together. So you want to find a way of representing the amplitude which is consistent with unitarity, regardless. Okay? It doesn't matter how many resonances there are. And that, a way to do that, or a step in that direction, is called the K-matrix. So let's go back to one channel. So how to solve? You solve using the K-matrix. So let's see how we do that. Let's go back to one channel. And when there is only one channel, this was elastic unitarity. So to emphasize there's only one channel, the initial one is number 1 and the final one is number 1. Now, can we find a way to satisfy that equation that will actually enable us to see how to do it for any number of channels? So let's consider 1 over the amplitude. Now 1 over the amplitude, you all learned how to do this. The easy thing to do is multiply top and bottom by the complex conjugate. So you know that's true. And now let's take the imaginary part of 1 over the amplitude. That's equal to the imaginary part of this quantity. But the imaginary part of the complex conjugate of a function is minus the imaginary part of the function. So this is minus the imaginary part of T11 over mod T11 squared. But what did elastic unitarity tell us? It tells us that the imaginary part of T11 is equal to rho 1 times mod T11 squared. So this quantity here is just a kinematic factor. It's just minus rho 1. So it says the imaginary part of the inverse of the amplitude is a known function. You don't have to do an experiment. You already know what it's going to be. So the only freedom can be in the real part. And the real part, we define the real part of 1 over T11 equal to something called 1 over K11, where K11 is the K matrix, where K11 is real for real values of S. Then it satisfies that equation. But now you see, this is what experiment's going to determine, and unitarity is automatically satisfied by writing 1 over T11 equals 1 over K11 minus I rho 1, which is the same as writing T11 equals K11 over 1 minus I rho 1 K11. So unitarity went and fixed the imaginary parts of the inverse of the amplitude, and K11, any K11 you like, will now automatically satisfy elastic unitarity. So if you're in a region of elastic unitarity and you want to parameterize your experimental data, doesn't matter, you don't have to know whether they're resonances or backgrounds or whatever. You parameterize this quantity K11 in any way you like. And in fact, this K11 doesn't have any physical significance, only T11 does. Now, we have to stop in a minute, and I need to get to a place where we can stop. Now, in the case of one channel, this K11 is called the K matrix. Why is it the K matrix? Because it generalizes to any number of channels. What you can show, and a nice little exercise for you to do, is to show that those three unitarity relations on this side of the equation for any number of channels the imaginary part of T now as a matrix, so imaginary part of T to the minus 1, where T is a matrix in this case, T would be equal to the matrix T11, T12, T21, T22, and because of time reversal invariance, T21 equals T12. Okay. Now you can show that the imaginary part of the inverse is equal to minus the matrix of rows. So in the case of two channels, what does that mean? It's the matrix row 1 and row 2, where those elements are 0. And then it tells you that the imaginary part of the inverse is a known thing, and so you define that the real part of the inverse of the amplitude is the inverse of what is called the K matrix. And this is again a matrix with real elements with real elements, otherwise it wouldn't satisfy that equation, real elements, but only for real values of the energy. And once you've seen that it works for two channels, then you can believe it'll work for any number. Now, I maybe just write one more equation and then or a couple more equations. So if you do that, then you can write that T11, which satisfies that equation, is K11 minus I rho 2, the determinant of the K matrix, over some denominator which I'll write in a minute. And T12 is equal to K12 over the same denominator, and then probably just by changing ones to twos, you know immediately what this one is. And each one has the same denominator. So in this particular case, those three equations that I've written there with the same common denominator automatically satisfy those three equations. Now, I have to have two more sentences. Resonances, I told you, or states in the spectrum, are poles in the complex energy plane. Poles in the complex energy plane correspond to zeros of denominators. So what you see is that if there is a resonance, the rho or any resonance, that appears in this channel, it will automatically appear in the other channels, because there will be a zero in delta at that particular complex value of energy, and it will appear in each of them. So it ensures that the poles of the S matrix transmit from one process to another that are allowed by quantum numbers. And by definition, these have the same quantum numbers, otherwise they couldn't couple to each other. So poles are zeros of delta. And they are in a common position for all channels to which they couple. So the rho resonance has the same pole in the complex energy plane regardless of the process that it appears in. Now, these K-matrix elements are just a convenient way of satisfying unitarity. They are auxiliary quantities. Only in models do they have some significance of their own. In other words, you can parameterize data in any way you like, with any parameterization of the K-matrix elements. They can have poles on the real axis, or it can be polynomials, and you can have any combination of them. As long as you describe the data, you will find that the poles of the S matrix, or the poles of the T matrix, the physical poles, are always in the same place, however you parameterize them. The parameters of the K matrix don't mean anything except in a model. If you knew what QCD actually was, then you could know what they are. But without that, they're just a convenient way of satisfying unitarity. The last sentence is that by doing this, any particular channel with a particular set of quantum numbers will in general have an infinite number of resonances in it. They are all in there all at once. You don't do what Antimo Polano did yesterday, namely add one resonance in a form of a Breit-Wigner, add another one, add another one. If they have the same quantum numbers, they're all encoded in one amplitude. And the virtue of that is unitarity is automatically satisfied, whereas in Antimo's amplitudes, they are not, unless the resonances are all well separated from each other and the backgrounds are essentially very small. Okay, maybe that's a good place to stop. Questions? No? Maybe come back with questions?